Ahoy, me hearties! Welcome to Real World Crypto 1721. It is me pleasure to give this talk entitled Is Isogenies for Real? And I would like to take this occasion to thank the organizers for inviting me and for offering me crew a fine barrel of West Indies rum.
So, you all know that contemporary cryptography lives and dies by the elliptic curve. Elliptic curves give us all we could hope for: a hard discrete logarithm problem, reasonable speed, compact parameters, well-understood side-channel countermeasures, and even pairings. But all good things must come to an end, and you all have heard of the menace looming over elliptic curves and discrete logarithm in general: the quantum computer. You have probably heard about NIST post-quantum competition and the various families of encryption and signature schemes supposed to be resistant to quantum attacks. In pole position, we have lattices and codes for encryption, multivariate polynomial systems and lattices for signatures. But I'm here today to talk about another family that's been making the buzz recently. No, it's not the Kardashians. I'm talking about isogeny-based cryptography. When we talk about post-quantum isogeny schemes, we mainly talk about two distinct but related families of schemes and security assumptions. To my left, SIDH, the key exchange and related schemes based on the full supersingular graph. To my right, C-side. Yes, these things has to be pronounced C-side. The family of schemes based on the action of a quadratic imaginary ideal class group on the subset of supersingular elliptic curves defined over a prime field. C-side is a direct descendant of the very first isogeny-based schemes, the family of schemes based on the hard homogeneous spaces framework of Couvaigne. Couvagne's work was not published at the time, and it's only 10 years later that isogeny-based cryptography really took up. First, Charles Goren and Lauder introduced supersingular isogenic graphs in cryptography to construct collision-resistant hash functions. Then, Rostovtsev and Stolbunov rediscovered Couvagne's scheme and were the first to suggest that it may be quantum safe. The SIDH key exchange only came some years later as a sort of mashup of the ideas of Couvagne, Rostovtsev and Stolbunov on one hand and of Charles Goren and Lauder on the other hand. Its importance lies in being the first efficient isogeny-based key exchange scheme, and it is currently the only isogeny-based candidate in the third round of NIST's post-quantum competition, under the name of Supersingular Isogeny Key Encapsulation, or SIKE. Since a few years, the field of isogeny-based crypto is booming. The recent discovery of C-side, the other efficient isogeny-based key exchange scheme, has been an amazing catalyst for the development of the field. A considerable effort has gone into designing efficient isogeny-based signatures, something that is only coming to fruition now. Let me stress now that SIDH and C-side give rise to two separate and incomparable families of isogeny-based schemes. To take an example from the lattice world, they are as related as NTRU and ring LWE, and possibly even less. Each has its own strengths and weaknesses, which I am going to discuss next. In the meantime, to complicate things, several other interesting isogeny protocols have emerged, which are neither based on SIDH nor on C-side. I'll just mention here Galbraith, Petit and Silva signature scheme, and more importantly its successor SkiSign, which sets a record for combined signature and public key size in the arena of post-quantum signatures.
Would you like to see?
Yeah! So let's start from the beginning. What is an isogeny? Isogenies are morphisms of elliptic curves. That is, algebraic functions from a curve to another curve that preserve the group structure. By algebraic, I mean that isogenies are defined by ratios of polynomials. The higher the degree of the polynomials, the more complex somehow the isogeny. Preserving the group law means exactly what you would expect. Isogeny of A plus isogeny of B equals isogeny of A plus B. Said otherwise, isogeny and scalar multiplication commute on the points of the elliptic curve. we say that two curves are n-isogenous if there exists an isogeny of degree n between them. Isogenies are as fundamental to the study of elliptic curves as matrices are to vector spaces. They basically control all algebraic properties of elliptic curves, their group structure, their endomorphism ring, their pairings. Take as evidence the famous Serre-Tate theorem: two elliptic curves are isogenous over a finite field if and only if they have the same number of points. Makes you wonder why no one told you about them before, doesn't it? In my view, isogeny-based crypto starts at the moment you stop looking at a single elliptic curve and its isogenies and enlarge your perspective to consider all elliptic curves with isogenies between them. This is what we call an isogeny graph, and in truth, there is more than one cryptographically interesting way to construct them. Indeed, the first big difference between C-side and SIDH is the kind of isogeny graph involved. But first we need to get something out of the way. All elliptic curves is really too much, as they contain too much redundant information. Instead, we like to classify elliptic curves by their isomorphism class. An isomorphism of elliptic curve is just a linear transformation that maps points one to one. And you may know that the J invariant classifies elliptic curves up to isomorphism. Usually in an isogeny graph, vertices are J invariants, representing an isomorphism class of elliptic curves, and edges are isogenies between the curves, up to composition with isomorphisms. In a typical graph, we also put some constraints on the degree of the isogenies. For example, the isogeny graph to use in SIDH has for vertices all isomorphism classes of supersingular elliptic curves, and for edges, all isogenies of degree either 2 or 3. In C-side, instead, the vertices are the isomorphism classes of supersingular elliptic curves defined over a prime field with p elements. The restriction to the prime field is important. The edges are all isogenies of degree taken from a fixed list of small prime numbers. For example, you can think of all primes from 3 to 400 and something. From now on, I shall call these two kinds of supersingular graphs the SIDH graph and the C-side graph, even when they are used in situations unrelated to both C-side and SIDH. Other names you will hear are the full supersingular graph and the FP-restricted supersingular graph. These two graphs pervade modern isogeny-based crypto and underpin a number of different security assumptions used to build protocols. But before moving to these security assumptions, a word about non-supersingular graphs. Why do isogeny cryptographers show so little love for ordinary isogeny graphs? If you come from classical cryptography, you may know that supersingular elliptic curves are considered insecure for ECC. So why is it the other way around for isogenies? First, the security of classical ECC is clearly unrelated to that of isogeny-based cryptography. Second, the original Couveigne-Rostov-Sestolbunov proposal was in fact based on isogenies of ordinary curves. Unfortunately, isogeny computation between ordinary curves are currently too slow for cryptographic application, whereas supersingular curves open the way to a few crucial algorithmic tricks that make all the efficiency of supersingular isogeny-based crypto. Ordinary isogeny-based crypto is not impossible, it's just that we are not there yet, and we may never be. So, if the security of isogenies is not based on the discrete logarithm problem, what is it based on? Informally, we say that all these schemes are based on the hardness of pathfinding in isogeny graphs, but in reality there is a great variety of different pathfinding problems involved. The ideal pathfinding problem looks something like this. Given an isogeny graph of elliptic curves over some finite field Fp, given two random isomorphism classes of elliptic curves in the graph, find a path in the isogeny graph joining them. Unfortunately, only C-side and the associated signature schemes are based on the pure form of this problem, the isogeny graph in question being the C-side graph, of course. We shall see, however, that being based on a clean pathfinding problem does not make C-side immune to powerful quantum attacks. SIDH, instead, is based on a more constrained problem in the full supersingular graph. Indeed, there, the two curves are not taken at random from the set of vertices, but at a rather short distance from one another in the graph, about half the typical distance of two random vertices. Even more concerning, both SIDH and Psych need to publish more information than just the start and the arrival curve. Together with these comes information on how the secret isogeny acts on some subsets of points of the elliptic curves, something that we call the torsion point images. We currently do not know how to exploit this additional information to break Psych, but attacks exploiting the same kind of information against hypothetical variants of Psych do exist. Yet another problem is needed to prove the security of the Charles-Goren and Lauter hash function. Here, instead of looking for paths, we look for cycles in the isogeny graph. More precisely, given a starting elliptic curve in the graph, collision resistance of the hash function reduces to finding a cycle passing through the curve. Second preimage resistance is similar. Given an isogeny path from some curve to some other curve, find an alternate path between the two. The alternate path problem is also crucial for the security of some other non-post-quantum isogeny-based schemes. I shall mention them later. But so, how hard is the pathfinding problem exactly? How does one build key exchange on top of it? To understand it, we may build a graph that relates to discrete logarithms in a group. Let's take an elliptic curve with group of prime order Q, and let's create a graph whose vertices are all the points of the curve, except the point at infinity. Now we connect 2 points A and B with an edge whenever A is equal 2 times B. We may do the same with A equal 3 times B, A equal 5 times B, etc. Now, given a generator G and another point H, finding a path from G to H gives a solution to the discrete logarithm of H to base G. If the graph is well connected enough, shortest paths between points will be of polynomial length, and we may thus say that the pathfinding problem in this graph is equivalent to the discrete logarithm problem of the elliptic curve. Does this graph look familiar? Yes, it has exactly the same structure as the seaside graph. So what do these graphs have in common? Mathematicians call these Cayley graphs, or more seldom Schreier graphs. I shall prefer the second name because it does better describe the seaside graph. In this example, we have two groups at play, the group of points of the elliptic curve and the group Z mod Q of the scalar multipliers. We say that Z mod Q acts on the points by scalar multiplication. But who is in play instead in the seaside graph? The vertices are, as we know, isomorphism classes of elliptic curves. Definitely not a group. You cannot add two isomorphism classes, of course. Okay, where is the group then? A venerable theory called the theory of complex multiplication tells us that a group is lurking behind the seaside graph. It is not Z mod Q, it is not the group of points of an elliptic curve, it is rather a class group of an imaginary quadratic number field. Okay, now don't get scared. You don't need to know what an imaginary quadratic number field is or what a class group is to use seaside. The important point is that we again have what mathematicians call a group action. Of a group, the class group, onto a set, the set of isomorphism classes of Singer curves. But given a group action, how do we do key exchange? It's very simple and it mimics classic Diffie-Hellman. Alice and Bob each take random paths in the Schreier graph. They exchange the arrival vertices, then reapply the same random paths starting from each other's vertex. Here, by the same, I mean the same element of the class group that's acting on the supersingular set. The magic of group actions guarantees that Alice and Bob secretly land on the same vertex, which they can then use as shared secret.
But is it quantum safe?
Confused, huh? If pathfinding is equivalent to discrete logarithm, and if discrete logarithm is broken by Shor's quantum algorithm, why is seaside not broken too? Somehow, the strength of seaside comes from the fact that the vertices of the graph do not form a group. Unlike elliptic curve points, you can't meaningfully add them together. This is sufficient to stop Shor's algorithm, as far as we know. But the class group acting on the vertex set is also the weakness of seaside. Indeed, if Shor's algorithm does not apply, a different quantum algorithm due to Kuperberg does apply. Kuiper-Bregg algorithm has sub-exponential complexity in exponential of square root of the size of the group. It thus does not count as a total break for C-side. It nevertheless causes quite some headaches to cryptographers when they try to quantify its quantum security. Indeed, you may have seen a stream of papers in the last few Eurocrypt conferences claiming wildly different security levels for the same exact C-side parameters. Research on the exact quantum security of C-side is still a very active area, and a consensus has yet to emerge. And the SIDH? Well, you may have noticed that the SIDH graph looks quite different. Indeed, for SIDH, there is no longer a group action on the set of isomorphism classes of supersingular curves. In truth, there are lots of group actions by different class groups on different subsets of the vertex set. When they interact together, these different group actions get jumbled together to an extent that is impervious to Kuiper-Bregg's algorithm. Indeed, the best known algorithm for solving the pathfinding problem in the SIDH graph has exponential complexity. But it's not only Kuiper-Bregg algorithm that gets confused in the process. The Diffie-Hellman-like key exchange we sketched previously also breaks down completely. To recover some algebraic structure and ensure the existence of commuting paths for Alice and Bob, the groups of points of the elliptic curves, which were completely forgotten in C-side, come to our rescue in SIDH. I am not going to explain here how SIDH ensures that Alice and Bob's paths commute. There are excellent tutorials for that, like Supersingular Isogeny Key Exchange for Beginners by Craig Costello. Suffice to say that this trick does not come for free, as Alice and Bob need now to exchange more information, which makes public keys slightly larger and, more importantly, potentially paves the way to specialized attacks. In conclusion, no isogeny is perfect. SIDH, aka Psych, has better understood quantum security, but is based on a somewhat ad hoc pathfinding problem, which is a bit concerning. It is clearly the more mature system and a good fit for NIST post-quantum competition, but has its flaws and limitations. C-side is at the same time older and younger than SIDH. Older because of the original idea by Couvain, and younger because of the recent move to supersingular isogeny graphs. Its quantum security is a complicated matter, to say the least, and it would probably be a bad match for NIST competition. And it's not in the NIST competition, anyway. But C-side is also the only credible instantiation of a post-quantum cryptographic group action. No post-quantum construction comes as close to old Diffie-Hellman as does C-side, and for this reason, C-side is capable of advanced protocols which are nearly infeasible for lattices or codes, etc. Most notably, C-side is the only efficient post-quantum non-interactive key exchange, a fundamental component in non-interactive protocols such as those found in the Signal messaging app. But since we mentioned codes and lattices, how do isogeny-based schemes fare in comparison to other post-quantum candidates? It is probably well known that key size is the main marketing argument for isogenies. Psych has the smallest public keys and ciphertext among all NIST candidates in each category. On the other hand, Psych is notoriously an order of magnitude slower than other candidates, owing to the large number of elliptic curve operations it needs to perform. This puts Psych on the opposite of the spectrum compared to code-based schemes, which are very fast but have very large keys. Lattice-based schemes, as usual, come out as the most versatile of all post-quantum encryption schemes. C-side was originally instantiated with even smaller keys than SIDH, but progress in understanding Kuiper-Bregg's algorithm may bump these sizes to levels similar to SIDH. It is currently slightly, possibly unavoidably, slower than SIDH, and increasing key sizes can only widen the gap. When we move to signatures, the picture becomes bleak. SIDH signatures involve several hundreds of repetitions of SIDH. They are thus both slow and large. C-side signatures allow for some compromises in terms of size, but are even terribly slower than SIDH signatures. That is, unless one is able to compute the order of the class group acting on the C-side graph. This may come a bit as a surprise. I told you that we know there is a class group acting on the set of supersingular isomorphism classes, but I didn't tell you that this group is more or less hard to compute. It turns out that computing its order is doable in sub-exponential classical time or polynomial quantum time. More crucially, having done this pre-computation, C-side signatures can be sped up by a significant amount, producing a decent signature scheme named C-fish. The problem with this strategy is that the pre-computation is very expensive, or even undoable for larger parameter sets. As long as we don't have quantum computers, that is. When we compare with NIST candidates, it looks like isogeny-based signatures are not at advantage. But there is hope. We recently discovered SkiSign, a new kind of isogeny signature based on Isogenic Graphs, but exploiting completely different algorithms. SkiSign is currently quite slow for signing, but has acceptable verification time, and remarkably small signatures and public keys, comparable in size to RSA signatures.
Small keys, we got small keys here! See, nobody cares.
Well, yes, small keys are cool, but do you really need them? Let's look at NIST's call. Here we are talking public key encryption and signatures. So the first application that comes to mind is TLS. Now, you may remember the ostrich and the turkey experiment run by Cloudflare and Google. Over the course of 3 months, the two companies implemented in Google's Chrome browser and in Cloudflare's server infrastructure 2 TLS extensions featuring hybrid key agreements based on anti-error or SYK. They measured the latency of the TLS handshake using each variant and found out that the overhead of the lattice-based scheme is barely noticeable, whereas SYK adds a considerable amount of latency. But they also observed an inversion of the trend in the right tail of the distribution, where the slowest TLS connections are found. They attributed this to SYK's smaller keys, which are more likely to fit in the typical MTU, the maximum transmission unit of TCP packets, and are thus less affected by packet losses. NIST's selection of SYK as an alternate candidate sends a clear signal. For the most typical use cases, isogenies are unlikely to be the preferred choice. Too new and a tad too slow. There is the eggs in the basket argument, of course. If lattices or codes prove to be broken, isogenies may save the day. And so far, they've proven to be quite sturdy against cryptanalysis. But NIST's decision is also an acknowledgement that there may be specific scenarios where isogenies have the edge over other candidates. So, what would be a good use of SIDH? Some say small keys are good for IoT, where small storage and low bandwidth are the norm. But the high energy cost is even more problematic there, and available RAM is also an obstacle on contemporary IoT platforms. Without dedicated hardware acceleration, I doubt SIDH could ever be used on low-power devices. Other applications where speed is not paramount but size is could benefit more from SIDH. For example, some fancy encrypted storage. Blockchains come to mind, obviously. However, the main focus there is on signatures rather than encryption. This is where SkiSign could actually play a much bigger role if we can gain confidence in its security assumption in the coming years. Can C-side be a better choice than SIDH for any of these applications? I doubt it. For one, it's even slower than SIDH, and this appears to be an intrinsic limitation of the algorithm. Secondly, uncertainty around its quantum security makes it not ready for production yet. I simply do not believe that C-side will ever be preferable to SIDH for encryption or key exchange, even though it relies on a qualitatively cleaner security assumption. So, what is C-side good for? If we speak in terms of technology readiness level, SIDH is at level 6, whereas C-side is only at level 2. So, don't expect C-side in the real world in the next 10 years. But where C-side really shines is in its flexibility. SIDH is a rather rigid system from which it is difficult to obtain anything else than encryption or key exchange. Codes, well, we're still struggling to make signatures with them, although there's recently been some interesting developments. Lattices are obviously very flexible, but terrible in practice at some tasks, for example, threshold schemes. C-side, in contrast, is the only known instantiation of a quantum-safe cryptographic group action, a cryptographic tool close enough to discrete logarithms that several classic protocols can be easily translated to it, with essentially no knowledge of isogenies. I already made the example of non-interactive key exchange, a fundamental component of many non-interactive protocols, such as OPTLS or Signal. But there is also oblivious transfer, oblivious pseudorandom functions, threshold signatures, and many more. I invite you to read Cryptographic Group Actions and Applications by Alamati, Montgomery, Petranabis, and myself to learn more about Seaside and cryptographic group actions in general. In synthesis, I believe that for the moment, Seaside is only a cryptographer's toy, unfit for the NIST post-quantum call. But keep an eye on it for amazing applications, more advanced than just encryption or signatures. Finally, I need to spend a few words on a topic unrelated to post-quantum cryptography. Remember those random walks in the Isogeny graph? It turns out they have another interesting feature. Evaluating an isogeny chain is a strictly sequential operation. Isogeny walks used in post-quantum schemes are typically rather short, a couple of hundred of steps. But what if we take much longer walks, say thousands or millions of steps? Then we have an operation that takes predictably long time, similar to repeated squaring in a group. Combining this idea with classical pairings, we obtain interesting time delay primitives such as verifiable delay functions, time-locked puzzles, and a recently introduced one named delay encryption. These primitives have several applications in distributed protocols: randomness beacons, leader elections, auctions, voting, and are thus very attractive for, guess what? Blockchains. Now, these primitives are quite challenging to implement, but I wouldn't be surprised if, along with Psych, they were among the first to be deployed in the real world. In summary, isogeny-based cryptography is a very rich field, with a variety of different assumptions and constructions which can hardly be summarized in a single talk. Some of these, such as Psych, are already road-tested and essentially ready for production. Others require more research, but may prove to be invaluable to some advanced applications. I hope that this quick overview gave you a fair idea of what isogenies can offer and will motivate you to learn more about them.
Oi, the Medi knows his stuff. I always says, a pirate worth its salt must know some good old-fashioned misogyny. Say lo, and see ye at the next pirate conference.